Hello mathematicians, thank you for joining me today as we look at some more graphing. So last time we looked at x times x minus 2 cubed. Today what we're going to look at is how to graph x squared minus 9 over x squared minus 2x minus 3. So now what we recall from last time is that if we want to graph this, we should go through and we're going to actually find a lot of different information about the graph, and we'll use that to come up with a sketch of the graph that represents all the important information. So now when we were finding that information, remember that there was stuff from the original function we needed, there were things from the derivative, and there were things from the second derivative. So we're going to go through step by step and find each of those things. Alright, so as we look at a function, what we want to know is, well, first off, what is the domain of the function? What things actually make sense to plug in here and which ones don't? When we find the domain, we also want to think about, are there any vertical asymptotes or holes? We can also find any x or y intercepts, and then we can also look at the end behavior and determine if there are any horizontal asymptotes. If it has any of those features, we want to make sure to graph them. So to begin with, we should find the domain of this function, and notice that this is a rational function, so it's a polynomial over a polynomial. Therefore, the domain is all the places where the bottom is not 0. So if we want to find the domain, we should look at where is x squared minus 2x minus 3 equal to 0. And anywhere that's 0, we're going to find that that's not in the domain. So if we solve this, what we get is x minus 3 times x plus 1 is 0. So x is 3 and negative 1. So what we would get is that the domain of this function is x is not equal to 3 or negative 1. And so it would be defined everywhere else except for those points. Now that we know that we're not defined at those points, we should determine, are those points vertical asymptotes or are those points holes? Now, in order to find that, remember we're going to have a hole means that the limit exists, and a vertical asymptote means we're going to positive or negative infinity as a limit. So what we need to do is find the limits at 3 and negative 1. So now as we find the limit as x goes to 3 of x squared minus 9 over x squared minus 2x minus 3, what we want to do first is plug in 3. And if we do that, we get 3 squared is 9 minus 9 is 0 over 9 minus 6 minus 3 is also 0. So we have a limit of the form 0 over 0, which we learned was an indeterminate form. And so now the idea is that if we want to find what this limit is going to be, well, we could go back and we could do some factoring and canceling, but what we saw is that we could also use L'Hopital's rule. So I'm going to go ahead and use L'Hopital's rule and just say what is the derivative of the top over the derivative of the bottom. So if I take the derivative of the top, I'm just going to get 2x. And the derivative of the bottom is 2x minus 2. So what I can do is find my limit by plugging in 3 into 2x over 2x minus 2. And so if I do that, I get 2 times 3 is 6 over 6 minus 2 is 4. So I end up with 3 halves. Notice now that I got a number out, it means that my limit can't be plus or minus infinity, so I do not have a vertical asymptote here. So I must have a hole here. And so when we're graphing this, we're going to remember that we have a hole at the point 3 halves, and we want to make sure to actually plot that in as we're given the graph of the function. Now we also need to check the limit as x goes to negative 1 because that also wasn't in our domain. So if I plug negative 1 in, I get negative 1 squared is 1 minus 9 is negative 8 over, and now we know the bottom 0 because that's why we picked the point negative 1 as not being in the domain. So we get negative 8 over 0. Because we got a non-zero number over 0, this isn't an indeterminate form. We know that this is either going to be, well, from each side it's either going to be positive or negative infinity. So in either case, we're going to have a vertical asymptote. So I'm going to say that this limit does not exist. So we do have a vertical asymptote at x equals negative 1. And so again, we'll keep track of that so that when we're plotting this function, we can include that in our graph. Now, if we want to find the intercepts, the first one we can find is the y-intercept. For that, we're just going to let x equal 0 and find the function value. So f of 0 is 0 minus 9 over 0 minus 3 is just positive 3. So I have a y-intercept at positive 3, so I can make note of the point 0, 3 as I'm graphing this function. All right, so now if we want to find the x-intercepts, what we're going to do is we're going to let y equal 0 and solve for x. And so we get 0 equals x squared minus 9 over x squared minus 2x minus 3. Now note that we can multiply by the bottom as long as the bottom is non-zero. And so what we're going to end up with is we're going to get 0 is equal to x squared minus 9 as long as the bottom's not 0. Notice if the bottom's 0, we get 0 over 0 is undefined, but otherwise it's okay to multiply through. Now notice the bottom is 0 at 3 and negative 1, so I'm going to put in as long as x is not 3 or negative 1, then if 0 is x squared minus 9, the entire function will be 0. As we continue with that, we can factor that. We get x minus 3 times x plus 3. So either x minus 3 is 0 or x plus 3 is 0. So x is plus or minus 3. But now notice that at positive 3 we said that we can't have a 0 because we had an undefined function. So what we're going to get is that we're actually only going to have a x-intercept at x equals negative 3, because otherwise we ended up with a 0 over 0. So the next thing we need to do is find if there's any horizontal asymptotes. So what we're going to do here is we're going to find the end behavior, or what is the limit as x goes towards infinity or negative infinity. We'll start off as x goes towards infinity of x squared minus 9 over x squared minus 2x minus 3. If we look at this, what we end up with is infinity squared is infinity minus 9, infinity squared minus infinity, but a smaller infinity minus 3. Well, we end up with infinity over infinity. Because we get infinity over infinity, we can indeed use L'Hopital's rule. So what I'm going to do is just take the derivative of the top and the derivative of the bottom, and I'm going to get 2x over 2x minus 2. If we again look at this, we plug in infinity, we get infinity over infinity. So I'm going to have to continue using L'Hopital's rule. So now the limit as x goes towards infinity of 2x over 2x minus 2 is going to be the limit as x goes towards infinity. The derivative of 2x is 2. And 2 minus 0 is 2. So I get the limit as x goes towards infinity of 2 divided by 2 is precisely just 1. Therefore, since we got a number out, we get a horizontal asymptote at y equals 1. So as we're graphing, we now want to include that in our graph. Now notice we should also check the limit as x goes towards negative infinity, but if we do that, we would get infinity over infinity again, and then we would take the derivative. Here we would get negative infinity over negative infinity, but we would take the derivative of the top and bottom again and still get 2 over 2 is 1. So in both directions, we'll have a horizontal asymptote at y equals 1. All right, now that we found the information from the original function, we're going to move on to the first derivative. And so what I have here is I've given us the first derivative is negative 2 times x minus 3 over x plus 1 squared times x minus 3. Now I didn't go through and do that, but if you need extra help, remember we're going to use a quotient rule here. So I would go back to the video on the quotient rule and get some extra practice with that. However, if we assume that this is the derivative, remember we need to find critical points, intervals of increasing and decreasing, and any extrema along the way. So in order to do that, what I need to do is find where is this 0 or undefined. Based on that then, I can make a number line to determine where it's positive and negative, and kind of figure out if I have any local extrema. So the first thing I want to say is, where is my derivative undefined? And notice, as before, we have that the derivative is undefined. This is a rational function, so it's undefined if the bottom is 0. So this is undefined if x plus 1 squared times x minus 3 is 0. And so what we get is x plus 1 squared is 0, so x is negative 1. Or x minus 3 is 0, so x is 3. And so we get that the derivative is precisely undefined at the points that aren't in the domain of the function, which makes sense, because if we have a discontinuous function, we can't have a derivative. All right, now we can also find where the derivative is 0, so we're going to set this function equal to 0. Now, remember the same thing we did last time is that as long as the bottom's not 0, we can multiply by the bottom, and so what we're going to get is negative 2 times x minus 3 is equal to 0 times this is just 0, as long as the bottom wasn't 0. So that is if x is not negative 1 or 3. Now, if I finish solving this, I get negative 2 is never 0. X minus 3 is 0 at 3, so I get x equals 3. However, we said that x can't be 3 because the bottom was 0, and we ended up with a 0 over 0 there. Therefore, we would get rid of this point, and in fact, we'd have no places where the derivative is actually 0. We would just have the two places, negative 1 and 3, where the derivative is undefined. So we can use those now to find what our number line is going to look like. Alright, so now we have our number line defined. We have negative 1 and 3 are partition numbers, and so what we want to do is figure out what does this look like at each point in the intervals, and so I would pick something less than negative 1, like negative 2. Now if I look at this, I notice that x minus 3 over x minus 3 is going to be 1 as long as x is not 3, so I'm really just looking at the negative 2 over x plus 1 squared. Now I can make my life easier because I also know that anything squared is just going to be positive, and negative 2 is always negative, so I get a negative over a positive is always negative. So what I get is that in each of these intervals, my derivative is negative. What does that mean about my function? Well, it means my function is decreasing everywhere except for at negative 1 and 3. So I would say that f of x is decreasing on the interval negative infinity to negative 1, union negative 1 to 3, union 3 to infinity. Now while I have this up here, what I have any critical values is, notice that negative 1 wasn't in the domain, 3 wasn't in the domain, so neither of those would be critical values. Therefore, since we don't have any critical values, we can't have any extrema, so there will be no local extrema for this, there will be no critical values, but we do know that this will be decreasing over all real numbers except for negative 1 and 3. Okay, we've now finished up finding all the information we needed from the first derivative, so now we're going to find the information we need for the second derivative, and that is we're going to try to find inflection points in intervals of concavity. So to do that, we're going to start off the same way we did for the first derivative, is find where is the 0 or undefined. So I'm going to start off with undefined, and my second derivative is undefined if the bottom here is 0, that is x plus 1 cubed times x minus 3 is 0. So now again, that happens if x plus 1 cubed is 0, so that is x is negative 1. Or if x minus 3 is 0, so that is x is 3. So I have that. My second derivative is undefined at negative 1 and 3, which shouldn't be surprising now because my original function was undefined there, my derivative is undefined, therefore the derivative of the derivative, or the second derivative, is undefined. So we do get that my second derivative is undefined at those points. So now if I try to find where my second derivative is 0, I'm going to follow the same process. I can multiply by the bottom as long as the bottom is not 0. So I'm going to get 4 times x minus 3 is 0, as long as x is not equal to negative 1 or 3, because that was where the bottom was 0. In this case, we find that 4 is never 0, but x minus 3 is 0 and x equals 3. Again, though, we said that x can't be 3 because our second derivative is undefined. Therefore, I would get that my second derivative is never 0, just like my first derivative was never 0. Now, what that means is that I only have the partition points at negative 1 and 3. So now I'm ready to make my number line for my second derivative. Now, as I find my number line for my second derivative, I just want to pick points in each of these intervals and plug them into the second derivative. Again, I'm going to note that this is always 1 as long as x is not 3. So I'm just going to be plugging it into 4 over x plus 1 cubed. If I pick something like negative 2, I get 4 over negative 1 cubed. Negative 1 cubed is negative, so positive over negative is negative. If on the other hand I plug in something like 0, I get 4 over 1 cubed is just 4, which is positive. And if I plug in something like 4, I get 4 plus 1 is 5 cubed is 125. 4 divided by 125 is again going to be positive. So I get that my second derivative is negative from negative infinity to negative 1. And it's going to be positive from negative 1 to 3, union 3 to infinity. So what that means is that f is concave down on negative infinity to negative 1, and it is concave up on the interval negative 1 to 3, union 3 to infinity. Now, we want to note if there's any inflection points. If we look at negative 1, remember that negative 1 was not in the domain of the function, therefore it cannot be an inflection point. Furthermore, 3 was not in the domain of the function, so it cannot be an inflection point. So indeed, we will have no inflection points for this function, just like we had no extrema. Alright, so what I've done is I've taken the information we found and I've combined it into one chart. We noticed that the domain was x is not negative 1 or 3. We had a vertical asymptote at negative 1, whereas we had a hole at the point 3 3/2. We also had a horizontal asymptote at y equals 1. We had intercepts at the point 0, 3 and negative 3, 0. We knew that our function was decreasing everywhere except for at negative 1 and 3. It was concave down from negative infinity to negative 1, and concave up from negative 1 to 3, union 3 to infinity. So now the last thing I need to do is kind of make sure that I combine the derivative and the second derivative to get a shape. I mark off any points that I have and I play connect the dots. So now to get a shape, what I have is on this interval from negative infinity to negative 1, I am decreasing concave down. So a concave down function looks like that. The decreasing side is the right hand side. So over this interval, my function will have that shape. If I look at my next interval, negative 1 to 3, I'm going to be decreasing concave up. So concave up will look like that. And now the decreasing portion is the left hand side, so my function will look like that. Again, from 3 to infinity, I'm also going to be decreasing concave up. So I'm going to get that general shape. Now if I combine this together, what I want to do is just plot in these points. And so what I'm going to have is, well, I'm going to have at negative 1, I had a vertical asymptote. So I'm going to draw in a vertical line. I had a hole at 3 and 3/2, which is approximately here. So I'm going to draw an open circle to represent a hole. I had a horizontal asymptote at y equals 1. So I'm going to draw that in. I had a intercept at the point 0, 3. And I had an intercept at the point negative 3, 0. I'll put negative 3 on there. So I'll fill in that hole because we actually go through it. And now if I look at my shape, I just need to connect the dots. So here I want to show this asymptote and go through this point with this shape. So what this is going to look like is something like this. Now, if I look at this interval, I'm going to have this shape. So I'm going to go through this asymptote. I'm going to come down through this point and get to this point, all with that shape. So I'm going to get something that looks like that. Now, if I continue on, I still have the same shape, and I need to get to this asymptote. So I'm going to look something like that. So now if I combine that all together, I'm going to say I'm going to get a function that looks like this. Again, I'll plot in these points. I have a hole here, a function here, and so I want to make sure I'm approaching those asymptotes. And so that is a graph of my function, which was x squared minus 9 over x squared minus 2x minus 3. Thank you for watching. As always, I hope you learned something today, and I hope you enjoyed the process along the way. If you did, make sure to like the video and subscribe to the channel. It helps me to know which videos are helpful, and it helps other people to find these videos so that they can also get help. Thank you.